Hello again. This is the class video 15.2, meant to be watched after the video lecture 15.2 for Thursday. And we're going to do example problems from chapter 15, section 2, energy in simple harmonic motion, and section 3, angular simple harmonic motion. So first, let me briefly talk about the learning objectives for section 2 and jot down some of the key equations that we talked about in the video lecture. Okay, so with regard to energy in simple harmonic motion, for the standard spring block oscillator, remember what that means. Horizontal, frictionless x-axis, block of mass m, connected to one end of a spring of spring constant k. The other end of the spring is connected to a fixed wall. Displace that block from equilibrium, or give it a shove while it's at equilibrium. Point is, get it moving back and forth, and it oscillates with simple harmonic motion. Remember, that system is a system for which we have to understand everything. So one of the things we have to do is calculate the kinetic energy and the elastic potential energy at any given time. That comes from, for example, kinetic energy, 1/2 m of the block times its velocity squared, and then you substitute the formula for the velocity of such a block as a function of time, and you square it and multiply by 1/2 m. And here's the formula you get for the kinetic energy as a function of time. 1/2 m, angular frequency squared, amplitude squared, sine squared of omega t plus phi. And we showed a plot of that on a Wiley Plus animation in the previous video lecture. It oscillates like a sine squared, where sine squared itself oscillates between 0 and 1. So the kinetic energy oscillates between a minimum of 0 and a maximum of 1/2 m omega squared x max squared. So you can use this formula to calculate the kinetic energy at any given time. And the elastic potential energy, you start with 1/2 little k x squared, and then plug in the formula for x as a function of time, and plug in that k equals m times omega squared, and you get this formula. 1/2 m, angular frequency squared, amplitude squared, cosine squared of omega t plus phi. So in order to use that formula for t, of course you have to know all the other constants. You have to know m and omega and x max and phi. Then you can use these formulas. Another thing we have to be able to do for the spring block oscillator is apply conservation of energy to relate the total energy of the oscillator at one instant to the total energy at another instant. In other words, because the only force doing work on this system is the spring force, which is conservative, we use E mech 1 equals E mech 2, where we pick picture 1 and picture 2, and then apply this idea to solve for something that we want to know. It says we have to be able to sketch a graph of kinetic potential and total energy. I showed you that on the animation in the previous lecture. And lastly, for a spring block oscillator, determine the block's position when the total energy, i.e. mechanical energy, is entirely kinetic, and when it's entirely potential. Now that's a good one, but that's just physical concept understanding. You got the block oscillating back and forth about the equilibrium point in the middle, plus x max on one side of equilibrium, negative x max on the other, oscillating back and forth forever. Where in that back and forth motion is the mechanical energy entirely kinetic? No potential at all. Did you say when it passes through equilibrium at x equals 0? Because that's where the spring is neither stretched nor compressed, so no potential energy. And that's where it's moving its fastest. The energy is all kinetic. Where in this back and forth motion is the mechanical energy entirely potential energy? Did you say at either extreme point, at plus x max or minus x max? Because at those two extreme points, I have the maximum stretch or compression of the spring, and the thing is momentarily at rest. There is no kinetic energy, it's all potential energy. Okay, those are the key ideas. Now let's go straight to a Wiley Plus problem. Ready? Here we go. Oh, let me bring the words down just a little bit so you can see it. That would help. Here we go. Wiley plus problem. It says, we have a block, mass big M, 5.4 kilograms, and it's at rest on a horizontal frictionless table. It's attached to a rigid support by a spring of spring constant little k equal to 6,000 Newton per meter. That's a stiff spring. Along comes a bullet of mass little m equal to 9.50 grams. Watch out, grams. And moving horizontally with a velocity of magnitude v equals 630 meters per second. And that bullet strikes and is embedded in the block. We have a collision, don't we? What kind? Did you say completely inelastic? That's the answer. Okay. Assuming the compression of the spring is negligible until the bullet is completely embedded, we are to determine A, the speed of the block plus bullet immediately after the collision, B, the amplitude of the resulting simple harmonic motion, and C, the period of the resulting simple harmonic motion. Wow. So, you see what they're talking about? There's the block on the spring. The bullet comes in, bam, embeds itself inside the block, giving the block plus bullet some initial velocity, and then it's going to with simple harmonic motion because of the spring. We want the amplitude of that simple harmonic motion and the period. All right. Here we go. Okay, so first part A, the speed of the block plus bullet immediately after the collision. So we're going to have to kind of think of this as in two steps. 2 stages. The actual collision, duration of that is a tiny fraction of a second, and then the motion that occurs after the collision, which in this case is simple harmonic motion. But we've got to look at those two things separately because we'll use different physics to analyze those 2 stages. All right, so first we have to deal with the collision. I'm going to take picture 1 to be just before the collision, which is what's drawn here, okay? I'm going to draw now a picture 2, which is going to represent just after the collision. The bullet is now completely embedded in the block, but the block hasn't had a chance to move yet. That's important. So there's the bullet. There's the spring constant K. Block has not moved yet. So that's the block there. There's the bullet inside. And the whole thing, block plus bullet, will have some velocity I'm going to label big V. We have here a completely inelastic collision. All right? What physics do we use to analyze a collision where there's linear motion? Did you say conservation of linear momentum? That would be the correct answer. So, capital P initial x equals capital P final x, where the system is block plus bullet as far as the collision is concerned. Okay? Not the spring. The spring hasn't even been compressed yet. The collision has just ended with the bullet embedded. Okay? And so we're going to actually put that corner of the block at x equals 0, where the spring is uncompressed. But we're applying conservation of linear momentum. So picture 1 for P initial, picture 2 for P final. So in picture 1, the only thing that's moving is the bullet. It's got a mass little m, a velocity little v, so its momentum m times little v. That's P initial x. So that numerically must equal P final x. Now look at the second picture. I have a total mass, big M plus little m. Yes, the mass of the bullet, little m, is much smaller than the mass of the block, big M. But technically I need the total. And I multiply that by the final velocity. That means the velocity at the end of the collision, which I'm labeling big V. And I solve for big V. Little m times little v over big M plus little m. Let's put in the numbers. Now, we're told the mass of the bullet is 9.5 grams. Be careful. That's 0.00950 kilograms. Little v, 630 meters per second. Then big M plus little m is 5.4095 kilograms. Note the units of kilograms cancel, and we'll end up with units of meters per second. And it's going to be a lot less than 630 because now the bullet is embedded inside a big block. And we get a simple value of 1.11 meter per second, obviously to the right in our drawing. And that's how fast the bullet plus block combination is moving right when the collision ends and right when the simple harmonic motion begins. And that's what we're talking about in parts B and C. Part B asks for the amplitude of the resulting simple harmonic motion. So now, moving on to B. Okay. After the collision, we have simple harmonic motion of a block spring oscillator. And so we know that the mechanical energy of the oscillating system is conserved. So now I define a slightly different system. Block plus bullet plus spring. You must include the spring now because it's doing work and it's a conservative force. You can include the spring, by the way, in the first part, in the collision. You can do that because the spring doesn't do anything in the collision. It's not yet compressed. So you can include it up there if you wish. So here I'm going to write it this way. E mech initial must equal E mech final. And I'm going to take for the initial situation what's depicted in my picture 2, right up above, because that's when the simple harmonic motion begins. And for my E mech final, I have to decide what to use. But I'm going to call this picture 3, which I'm now going to draw. What do I want to pick for the final there? And then draw a picture representing it. Well, since I want the amplitude of the simple harmonic motion, which is the point of maximum displacement from equilibrium, then that's the picture I'm interested in. So there's the wall. There's x equals 0, where the simple harmonic motion began. But now the block-bullet combination is somewhere over here, where it is momentarily at rest. And I have a pretty highly compressed spring now, because that's the point of maximum compression, and therefore the point of maximum displacement from equilibrium. So that's x max. That's what I want to find. Okay, so let's now apply. E mech initial equals E mech final, and I want to see you be able to do it this way. For E mech initial, I'll write that as K initial plus U spring initial, and apply that to picture 2. For E mech final, I'll write K final plus U spring final, and I'll apply that to picture 3. Let's make sure you can remember picture 2. It's right there. Notice the spring is not yet compressed, so there is no potential energy, but the bullet block combination is moving, so there's kinetic energy. So for K initial, we write, I got to get this correct, 1/2, there's the mass, right, bullet plus block, and times big V squared. Picture 2, plus 0. There is no compression of the spring, so no potential energy. Equals K final. Now look at picture 3. Well, it's momentarily at rest, so K final is 0, but I have a compressed spring. So I need to remember the formula for spring potential energy. 1/2 little k, and the compression here is x max. So x max squared. And I'm going to solve for x max. I'll multiply both sides by 2. Those will go away. And then I'll divide both sides by k, and then I'll take the square root of both sides. You get x max equals big M plus little m times big V squared all over k. If you are so inclined, you could plug in numbers at this point, because you know big M, you know little m, you know big V. We just found that in part A, the velocity just after the collision, 1.11 meters per second. Don't put in the initial velocity of the bullet, 630. No, not even close. This big V is the velocity when the simple harmonic motion begins, which is when the collision has just ended. And of course, K, remember, is 6,000 Newton per meter. Now, another thing you could do, if you want to be a little bit more fancy, a little bit more advanced, is you could take this symbolic answer I have up above for big V. See it right there? Little m, little v over big M plus little m, and put that in there where the big V is and square it and simplify. You're welcome to try that if you want. If you do, the symbolic answer you get is little m times little v. Now that is a little v over the square root of k times big M plus little m, if you do that algebra correctly. So there is what I'm going to substitute numbers in. And there, that is little v. So that's 630 meters per second. But upstairs, that's just little m, mass of bullet only, 0.0095 kilograms. That's the m. Anyways, you plug all those numbers in, and you get 3.32 times 10 to the negative 2 meters. You check that on your calculator. Probably the way a physicist would write that is 3.32 centimeters. Not a big amplitude. Remember, it's a very stiff spring. Okay? So we applied conservation of mechanical energy to find the amplitude of the simple harmonic motion. Part C asked for the period of the simple harmonic motion, capital T. I will just remind you that the period is 2 pi over this quantity called the angular frequency. And for a block spring system, the angular frequency has a very clear formula. Square root of spring constant over total mass, which in our case would be big M plus little m. So I'm going to plug that expression in for the omega in the period formula, and I get this expression for the period. 2 pi times the square root of big M plus little m all over the spring constant, K. And then you plug in numbers. You plug in big M, little m, K. Don't forget the 2 pi out front. You get a period of 0.189 seconds. Very short period because the spring is very stiff, so it oscillates very fast. Okay? Okay, so that's a Wiley Plus problem involving conservation of mechanical energy and a block spring oscillator. Now we transition, like the video lecture, to what's called an angular simple harmonic oscillator, also called a torsional pendulum. And that's where you take a disc-shaped object, well, it doesn't have to be a disc, just some kind of solid object, suspended on some kind of a strong wire from fixed support, a wire that you can twist and will untwist when you let go, and then you just take that object, turn it, thereby twisting the wire and let go. Okay? And you get angular simple harmonic motion. Here are our learning objectives. You have to describe the motion. Well, I just did. You paint a reference line on the object. You have a scale right there so that you can read the angle on that reference line and call it theta. And theta will oscillate with time with simple harmonic motion. 15.3.2. For an angular simple harmonic oscillator, apply the relationship between the torque tau and the angular displacement theta from equilibrium. That, as I mentioned in the video lecture, is the angular version, or the torsional version, of Hooke's law. Instead of F equals negative kx, which is a spring force, we have torque equals negative kappa, kappa not K, times theta, where kappa is called the torsional constant for the wire. 15.3.3. For an angular simple harmonic oscillator, apply the relationship between the period, capital T, or frequency, little f, the rotational inertia I, and the torsion constant kappa. Okay, we wrote that down by applying Newton's second law. The angular frequency for a torsional oscillator is the square root of the torsional constant kappa over the rotational inertia of the object. Then, using the fact that period is 2 pi over omega, and substituting that expression for omega, you get a handy formula for the period of a torsional oscillator, 2 pi square root of rotational inertia over torsional constant. And then just remember that frequency f is 1 over period. So find the period and then just invert it. You've got the frequency. All right, 15.3.4. For an angular simple harmonic oscillator, at any instant, apply the hallmark relation between the angular acceleration alpha, the angular frequency omega, and the angular displacement theta. The hallmark relationship for simple harmonic motion, angular version, is simply this. At any given time, the angular acceleration alpha is equal to the negative of the angular frequency squared times the angular displacement. Okay, that means simple harmonic motion for the variable theta. Last learning objective is to just be careful, basically, to distinguish between the oscillator's angular frequency omega, right there, okay, and the d theta dt, the rate at which its angle is changing, because they're not the same. All right, the rate at which the angle is changing is d theta dt. The theta itself as a function of time comes from this formula, theta max cosine of omega t plus phi, as we talked about. So the rate at which that angle is changing would be d theta dt, got to take the time derivative of that and use the chain rule. All right, let's do a Wiley plus problem for angular simple harmonic motion. Might look a little bit different because it's actually reverting back to an actual application, an actual angular simple harmonic oscillator, even if it is an antique. It's going to talk about the rotation of what's called the balance wheel of an old-fashioned watch, of the old-fashioned kind before electronic watches when they were mechanical. And you would have a horizontal wheel with a kind of a spring with an axis through the center, and it would oscillate. And that's exactly what we're talking about here. Okay? And so let's suppose we have one of these balance wheels oscillating with angular simple harmonic motion with an angular amplitude, theta max, of pi radians and a period of half a second, 0.5 seconds. We're supposed to find a number of different things for this motion, starting with the maximum angular speed of the wheel's rotation. Let me start with a couple of sketches. We'll do a top view. Don't worry too much about this balance wheel. Just think of it as looking like some kind of like a disc-shaped object with an axis of rotation through its center, and that it oscillates about that axis coming out towards us. And imagine that we have a reference line, I'm drawing it here in red, that's been painted on the wheel. It goes from the axis out to the edge. And then we've got a fixed label for where theta equals 0 is. That's equilibrium for the wheel. If I put it there and left it alone, it would just stay. But somehow we get this wheel oscillating about the axis right there in the middle. So at some time t, that reference line on the wheel compared to where theta equals 0 is, will have turned. And you can talk about that angle, theta, at time t. Okay? Now it's changing with time. So that whole thing is rotating either clockwise or counterclockwise. It's oscillating. So sometimes it's clockwise, sometimes it's counterclockwise. And in fact, the equation that relates that angular displacement as a function of time is the one I just wrote down for angular simple harmonic motion. Theta max cosine of omega t plus phi. And I am told what the theta max is. The maximum angular displacement from equilibrium is pi radians. That means that red line can go all the way over to there. That would put it at pi radians from theta equals 0. And then it goes around the other way also to pi. All right, what else do we know? What about that angular frequency omega in that formula for theta? Well, that's 2 pi over the period. And I'm told the period is half a second. The 2 pi is in radians, by the way. Period is half a second. 1 over a half is like multiplying by 2. So that's really 4 pi. And the units are radians per second. So there's the angular frequency. I know that. So I know the theta max. And I know the omega. I don't know the phase angle phi, though. But that's what I know. Let's see if we can answer part A. Find the maximum angular speed of the wheel's rotation. So when we talk about an angular simple harmonic oscillator, by angular speed, what we mean is d theta dt. That's what we mean, and that's how you should denote it. Don't use the symbol for this, omega, because that's the symbol for angular frequency. Just call it d theta dt when you have an angular simple harmonic oscillator. But then take the formula for theta of t, take the derivative of it using the chain rule. For d theta dt, you get negative omega theta max sine of omega t plus phi. But they want the maximum angular speed. Speed, not angular velocity. So what they're really asking for is absolute value d theta dt maximum. Angular speed is magnitude of angular velocity, absolute value, and I want the biggest that can be. The thing to note is look at the formula for d theta dt right here and figure out what the biggest that can be is. It's that product right there, omega times theta max. That's the biggest I can get. You see that? Because the biggest the sine can be, it's oscillating, but the biggest it can be is 1. So the biggest d theta dt can be is 1 times omega theta max. That's very important to see that. So d theta dt absolute value maximum is just the angular frequency omega times theta max. Well, omega is 4 pi, and theta max is pi. So yes, that's the rather weird-looking combination, 4 pi squared, but you put that in your calculator, I get 39.48. The units would be radian per second. I'll round that to 3 sig figs. 39.5 radians per second. Okay? That's the fastest the angular speed of the wheel can be. 39.5 radians per second is pretty hefty for something as small and delicate as a balance wheel in a mechanical watch. What did part B ask for? Get it back. Find the angular speed when the angular displacement is pi over 2 radians. So now what we're talking about is the instant in time when that reference line that we've painted on the wheel is right there. so that theta of t is pi over 2 radians. Notice I don't know what t that is when that happens, but that's the picture I'm interested in. So what I want is what they call the angular speed. That's d theta dt magnitude, or absolute value, for the moment when the theta is pi over 2 radians, like my picture shows. Well, I'm going to take my theta of t equation, and I'm going to write it like this. Theta equals theta max cosine of, I'm just going to write that whole blob, omega t plus phi, as phase. It's called the phase, the argument of the cosine. And because I don't know what that number is. I don't know what the t is when this happens. I don't know what the phase angle phi is. So I'll just say the argument is called phase. That stands for omega t plus phi. But I don't know the t and the phi, so I can't give you a number. I'm just going to write it as phase. But I know what theta to put in. Pi over 2 radians. And I know what the theta max is. Pi radians. So I can just solve that for that quantity phase. You see what I'm saying? Cosine of that quantity called phase is just theta over theta max, but the theta is pi over 2 radians, and the theta max is pi radians. The radian part cancels, it's dimensionless anyways, and that ratio is just 1/2. And then I can get the value of the phase by taking the inverse cosine of both sides with my calculator in radian mode. And I'm taking the inverse cosine of 1/2 with my calculator in radian mode. What you need to realize is that turns out to be pi over 3 radians. Okay, now I know what the phase value is inside the cosine. And I can now tell you what the absolute value of d theta dt is. That's the absolute value of negative omega x max sine of the phase quantity. It's the same phase that was inside the cosine. So, take away the negative sign out front. The omega is 4 pi. The theta max is pi. And I'm taking the sine of the phase, which is pi over 3 radians. I put that into my calculator. I get 34.19 radians per second. If I round it to 3 sig figs, 34.2 radians per second. Note the angular speed at this location is less than the d theta dt max, the maximum angular speed. That's good. It can't be bigger than what we found to be the maximum angular speed, because we found that to be 39.5 radians per second. So the d theta dt for the picture right there in B is 34.2 radians per second. Okay, one more part, C. Find the magnitude of the angular acceleration at angular displacement pi over 4 radians. So now what's the picture? So now, there's the axis, there's the reference line. Now, the angular displacement, theta, is pi over 4 radians, halfway between 0 and pi over 2. And I want the magnitude of the angular acceleration when that's the theta. I'm going to use what the book calls the hallmark equation for simple harmonic motion, angular form, which is angular acceleration alpha equals negative angular frequency squared times angular displacement. Because I know the omega and the theta. But I want absolute value of the angular acceleration. So that'll be omega squared times theta. Remember, the omega is 4 pi, so that gets squared. The theta is not theta max, it's the theta of the picture here, because I want the alpha for this picture. And that theta is pi over 4. So that turns out to be, if you look carefully, numerically equal to 4 pi cubed. And that turns out to be 124. And that would be radians per second squared, which is pretty hefty. This little wheel is undergoing some pretty large angular accelerations. This is just for that position. It's not even the maximum angular acceleration you get. That'll be when theta is at theta max, which is 4 times this theta. So the maximum alpha, absolute value, is 4 times 124, or 496 radians per second squared. Okay, so that's all. That's a typical Wiley plus problem for an angular simple harmonic oscillator. Okay? All right. And the next topic, actually the last topic in chapter 15, is we're going to come back and look at a pendulum. So that'll be the topic of the next video.